All right, welcome. Today we're going to dive into a machine learning tool that's actually super intuitive because, it works a lot like our own brains. We're talking about the decision tree. It's all about making really complex choices by just asking a series of simple yes or no questions. So let's get right into it and see how it works. So, let's start with the big question, right? When you're faced with this just mountain of data, how do you actually teach a machine to see the patterns hidden inside and make smart predictions? Well, as you can probably guess, it's almost never as simple as just drawing a straight line through it all. Yeah, think about it. Most patterns in the real world just aren't straight lines. Let's take a new medicine, for example. A small dose, maybe it has a tiny effect. A medium dose could be perfect, right? But then a high dose, that might actually be harmful. You get this kind of up and down curve. That's a classic nonlinear relationship. And a simple straight line model, it would completely miss the whole story. So we clearly need a tool that's way more flexible than that. And that is exactly where decision trees just shine. See, instead of some crazy, complex formula, they work by copying how we humans actually think. It's kind of like deciding whether or not to grab an umbrella. You ask yourself, okay, is it cloudy? Yep. Next, does the forecast say it's going to rain? It does. All right, final decision. Take the umbrella. See? It's just a sequence of simple questions that leads you straight to a clear answer. Okay, so every single decision tree has to start somewhere, and that starting point is called the root node. Just think of it as step one. It's where our entire messy, unsorted data set is just sitting there, waiting for that very first question. Now, from that root, we start to branch out into what are called decision nodes. And this is where all the action happens. Each one of these nodes is basically a question point. It asks a simple true or false question about one of the features in our data. Something like, is the blood pressure over 120? Or is the weather sunny? And that one question immediately splits our data into two smaller, more manageable groups. So you follow this path, right? You go from the root node through a few of these decision nodes, and eventually you're going to hit an endpoint. And these are called leaf nodes. This is the end of the line. It's where all the questions stop, and the final prediction is actually made. So if we're trying to predict heart disease, the leaf node is the thing that finally says high risk or low risk. It's the final destination for that particular journey through the tree. Okay, so the tree is built out of these questions. That makes sense. But how does it know which questions to ask? And in what order? That's the real magic here, right? This is the secret sauce behind how a decision tree actually learns. It's all about finding the absolute best, most informative question to ask at every single step to split the data. And the goal of every single split, every single question, is to make the groups that come out of it way more predictable. What we're trying to do is create subgroups that are as pure as possible. And when I say pure, I mean a group where basically all the data points belong to the same category. Think of it like sorting laundry. You want all the whites in one pile and all the colors in another. And take a look at this, because it shows the idea perfectly. Over on the left, you've got a bad split. See how the two new groups are still just a messy mix of orange and green? We haven't really learned anything new here. There's no clarity. But now, look over at the good split on the right. See that? It's done a fantastic job of separating most of the green squares into one group and the orange circles into the other. That split actually taught us something. That's what we call progress. So how does the machine actually measure this purity with math? Well, it uses a couple of really clever tricks. The first one is called the Gini index. You can just think of it as an impurity score. A Gini of 0 means the group is perfectly pure, all one thing. The higher the score, the more jumbled up it is. The other big one is called entropy, which is really just a measure of randomness or uncertainty. A super mixed up group has high entropy because you have no idea what you're going to get if you pick something out of it at random. So a good split is simply the one that causes the biggest drop in that Gini score or the biggest drop in entropy. The tree literally tries out all the possible questions and picks the one that does the best job of cleaning up the data. Now, all this power and flexibility, it comes with a pretty big risk. It's a trap that decision trees are, frankly, famous for falling into. It's called overfitting. And this is what happens when a tree gets a little too smart for its own good. It doesn't just learn the real patterns, it starts memorizing every little random bit of noise in the training data. So here, this is what we want to see. This is a healthy, sensible tree. It's simple, right? Just a few branches. It's learned the big, important patterns in the data. And because it's not trying to be overly specific, it's way more likely to make good predictions when it sees new data for the first time. And then there's this. This is the total opposite. This is an overfit tree. You can think of it as the perfectionist.
It's grown completely wild, with branches splitting over and over and over again, until it has a special, unique path for almost every single data point it was trained on, and that includes all the random noise and all the weird outliers.
So what's the big deal with being a perfectionist? Well, the problem is the tree has become so obsessed with the training data that it's memorized the noise, not the actual signal. It's created these incredibly specific if-then rules that just don't apply to anything else. So the moment you show it some new data, its predictions just fall apart. It's perfectly tuned to the past, which, ironically, makes it absolutely terrible at predicting the future. Okay, so if letting a tree grow until it's perfect is actually a really bad idea, how do we fix it? Well, the answer is a process called pruning. And it's exactly what it sounds like. Just like a good gardener snips off the weak or unnecessary branches to help a tree grow stronger and healthier, we do the same thing. We prune our decision trees to make them much better predictors. And there are basically two main ways to go about this. The first is called pre-pruning, or early stopping. This is like being a proactive gardener. You set rules ahead of time to stop the tree from growing too deep before it even has a chance to make a mistake. The other approach, which is really common, is post-pruning. This is the opposite strategy. You let the tree go wild and make all the mistakes it wants, and then you go back and strategically snip off the branches that aren't really helping. You're fixing the mistakes after the fact. And this whole process, this pruning, is really all about finding that perfect balance. We want a model that's accurate, of course, but also simple enough to work on new data. To do this, the algorithms use something called a complexity penalty. Think of it like a tax. For every new branch the tree adds, it gets a small penalty. So the goal is to find the tree that has the best accuracy after you subtract all those penalties. It basically forces the model to ask itself, is this new branch really worth the cost? So after all this work, building the tree, carefully pruning it back, what's the big payoff? Well, beyond just making predictions, one of the absolute greatest strengths of a decision tree is its transparency. A lot of machine learning models are like a black box. Data goes in, an answer comes out, and you have no idea why. A decision tree is the opposite. It can actually show you its work. It doesn't just give you an answer, it shows you the step-by-step logic it used to get there. And that transparency gives us something incredibly valuable. It's called feature importance. Basically, the model looks back at its own work, at all the splits it made, and it figures out which features, things like blood pressure or age, did the most heavy lifting, which ones were most effective at making the groups purer. If a feature was used a lot, especially at the top of the tree to make those big, powerful splits, it gets a high importance score. It literally tells us which factors were the real game changers in making the decision. And here's a perfect example of what that actually looks like in practice. Check out this chart. Let's say we're predicting heart disease risk. The model has gone through and calculated that blood pressure was by far the most important feature for making its predictions. Cholesterol was next, but not nearly as important, and age was a distant third. This is huge. It doesn't just give us a prediction, it gives us real, actionable insight into the problem we're trying to solve. All right, so let's zoom out for a second and give the decision tree its final report card, the pros and cons. As we've seen, the strengths are awesome. They're super easy to understand, they can handle all sorts of different data types without a fuss, and you don't have to do a ton of data prep. But on the flip side, the weaknesses are pretty serious. We've already talked a lot about how they love to overfit, and they can be a bit unstable. And that last point, piecewise constant, just means that a tree predicts things in steps or blocks. It can't predict a smooth, continuous line, which can be a problem sometimes. So look, a single decision tree definitely has some flaws, but this is where things get really interesting. Its true power isn't necessarily when it works alone. It's when we start thinking of it not as the final product, but as a fundamental building block for some of the most powerful algorithms in all of machine learning. And that brings us to one final, really powerful idea. We know that a single tree can be smart, but also kind of brittle and unstable. So that leads to a pretty obvious question, right? If one tree is this smart, what could a whole forest of them do? That question right there is the key that unlocks some of the most famous and powerful models out there, things like random forests and gradient boosting. But that's a story for another time. Thanks for joining me.